Let's use our knowledge of rolling without slipping to consider a solid cylinder rolling down an incline. Let's draw a diagram to get our mind around this. So we have a solid cylinder, it's rolling down an incline, we have some radius r, and we have some angle here of the incline phi. We know the mass is m, radius r, I already said, and we want to know what's the acceleration. To find the acceleration, generally what we'll do is we'll draw a free body diagram and use Newton's second law to write an expression that we can solve for acceleration. Here's a free body diagram. We include the forces acting on the cylinder. The weight of the cylinder acting downward, which is why it starts moving. The normal force that keeps it from passing through the ramp. And then the frictional force that, if it's rolling without slipping, is acting upward along the slope and is static friction. This is what makes it start spinning, is that frictional force. We align our axes with the slope to make our lives a little bit easier, and do a little bit of geometry to show that if the angle of the slope is phi, then the angle between my weight and my y-axis here is also going to be phi. And that lets us break down our mg into a component aligned with the y-axis of mg cosine phi, and one with the x-axis mg sine phi. Now let's write Newton's second law and see what we get. In the y direction, we get our sums of our forces equal to mass times acceleration in the y, which should be 0, because we're not coming off the surface here, we're rolling down the surface. We can plug in our y components here, n is going to be positive, and this mg cosine phi is going to be negative, and they sum to 0. We solve for the normal force, and we have an expression for the normal force, which is great, maybe we'll use that, but that doesn't have acceleration. For that, we need the sums of the forces in the x direction. Newton's second law in the x direction says that our sums of our forces are equal to mass times acceleration in the x, and this is what we want, that acceleration a. We can look at the force that's making us move, mg sine phi, that's positive, and then fs is resisting this, it's negative. And those sum to mass times acceleration. Here we have an equation with the thing we want, a, but we have a problem. We don't know our static frictional force here. If we just knew the static frictional force, then we'd be able to solve this for a. Just divide both sides by mass, we have an expression for a. So we need some way of finding this static frictional force. For that, let's turn to applying Newton's second law for rotation. This says that our sums of our torques about any point is equal to I alpha. And here I propose that we choose the center of mass as the point to sum our torques about. This means that weight doesn't appear, mg doesn't appear, and we're just left with fs and n. But n acts straight through the center of mass, so there's no lever arm, so it won't appear either. And we're just left with rfs, which I'm calling clockwise positive because this is trying to spin clockwise, how I've drawn it. So we have rfs is equal to I alpha, where that I is for a cylinder about its central axis there. We can solve this for the force of static friction, Fs, by dividing by r on both sides, and we end up with I alpha over r. Now we can go back here and say this is great. We can substitute in, well, we'll divide by m so that we get acceleration, which is what we want. And then we can substitute in now our Fs value. Substituting that in, we get an expression that looks like this, g sine phi minus 1 over m times I alpha over r. And we're almost there. We have an expression with an a and an alpha, and we don't know alpha. And you might be like, well, we don't know anything. We have no numbers. That's fine. We have mass and radius. So mass and radius are fine to be in our solution. I can look up in a table and it'll be in terms of mass and radius for the cylinder. G is a constant. Phi is a property of the system as well. So it's fine to have all of those things when we're trying to develop this formula that expresses what the acceleration is in terms of our system parameters. We just don't want things like alpha that aren't already a system parameter. Here's where we can pull in rolling without slipping. Rolling without slipping says that our acceleration is equal to r alpha. We solve this for alpha, that says alpha is equal to a over r, and we can plug this in for alpha. Doing so, we end up with an expression that has a equaling g sine phi minus I over mr times a over r. We have a twice in here, so we have to try and combine the a's onto the same side to then be able to solve for them. That means that we'll add this term to both sides so that we can get a's on the same side, and then we'll factor out an a from both of these terms over here, which leaves us with 1 plus ICM over mr squared. And then that equals g sine phi, leaving us just one more step, which is dividing by the coefficient here by a to get a by itself. A is equal to g sine phi over 1 plus our moment of inertia about the center of mass of this object divided by mr squared. And there's an interesting thing. You might be like, why didn't we substitute in for ICM way back here? Maybe that would have made our lives easier. Well, this, by not doing so, we have gotten a generally true statement for rolling without slipping as you roll down this ramp. So anything that's rolling without slipping down a ramp, whether it's a cylinder or a sphere or something else that can roll, will have this behavior. And now to get our behavior for the cylinder, we just have to find our center of mass, plug it in, do a little bit more algebra, and we'll end up with an expression. So if you end up seeing something like this again, you can do all this work again. It should be doable. Or you can hop to, well, I know that this is the behavior for this sort of situation. All right. We need a little bit more space. So let's start with where we stopped here. This is our generally true statement. And now we'll try and find it for this particular solid cylinder. That means we have to look up our moment of inertia for a solid cylinder, which is 1/2 mr squared. We can now substitute that in for the I center of mass. Do a little bit of algebra, cancel out the mr squareds here, and rewrite it to make it clear what's going on. We can combine the 1 and the 1/2 into 3/2. Dividing by a 3/2 is the same as multiplying by a 2/3. So we end up with our acceleration is 2/3 g sine phi. There we go. We have our acceleration, and because we're rolling without slipping, we know our angular acceleration as well. It's just going to be a over r, or 2g over 3r times sine phi. There we go. We have our acceleration. We're not done. We've got a part B. What condition must the coefficient of the static friction μs satisfy so the cylinder does not slip? All right, for this, let's look at our static friction. We know from before that our static friction was equal to I alpha over r. We can substitute in for alpha, where alpha is a over r, and we get I a over r squared. And we can substitute in that a value we just solved for to plug in this. And in fact, here, this is not the a value that we just solved for. This is our generally true a value. So again, we're going to try and find a generally true thing, and then we'll plug in our I center of masses afterwards. So this is my generally true acceleration for an object rolling without slipping down an incline. Let's simplify this a little bit. We've got an r squared that when we multiply it into each of these, we'll get rid of the r squared down here. We need to get rid of this m as well if we don't want nested fractions. So we'll multiply by m over m to just try and get rid of that. And that leaves us with an expression for the static frictional force of I mg sine phi over mr squared plus I. Okay, so what's the condition? The condition for slipping is that my force of static friction has to be less than or equal to μsn for static friction to hold. As soon as our force of static friction has to be greater than that, it can't be, because remember, this is our maximum static frictional force. This is where solving for that normal force earlier comes in handy. We can say that that normal force n is mg cosine phi, plug it in, and plug in our fs value from right here, and then solve for μs in terms of our system parameters. Oh man, that's glorious. Luckily, this algebra is not too bad. At this point, we divide by mg cosine phi, and we're left with μs having to be greater than or equal to I over mr squared plus I times mg sine phi over mg cosine phi. It looks like these mg's will cancel. Sine over cosine gives us a tangent, and we can write this like this. Our condition is that μs has to be greater than or equal to I times tangent phi over mr squared plus I. That's generally true. Generally true. For a cylinder, now we just have to plug in our I for a cylinder. This might seem a little bit like a lot of work. We maybe could have gotten by with a little bit less work if I hadn't insisted on doing this more generally. But hopefully having this as a general solution for something's rolling without slipping down an incline. What coefficient of static friction do I need for that to be true? Well, this gives you an equation. All right, so let's start with this and then continue on from there and say for a cylinder, I is equal to 1/2 mr squared. Plug that in. Do a little bit of algebra. It looks like those mr squareds will cancel because we can factor it out from the bottom and then cancel it out with the top, leaving us with 1/2 tangent phi over the quantity 1 plus 1/2. That adds to 3/2 as before, which as before is the same as multiplying by 2/3, or we can multiply by 2 over 2 to cancel those out. And we end up with our coefficient of static friction for a cylinder has to be 1/3 the tangent of phi, which is kind of a pleasingly simple expression to get out of kind of a algebraically involved problem.